This video is a review of the first 10 chapters in the quantum chemistry playlist. So starting with early quantum theory, we have several experimental situations where a quantization hypothesis was necessary to overcome the deficiencies of classical mechanics and thus quantization and quantum mechanics. We have examples like the photoelectric effect, where the kinetic energy of electrons ejected from metal only depended on the frequency of light and not its intensity. The Rydberg formula, where the spectral lines in hydrogen obey an empirical relationship of the difference of the inverse square of two integers. And then we have the Bohr model for the hydrogen atom, which proposed quantization for the angular momentum in the hydrogen atom. The de Broglie hypothesis, where de Broglie hypothesized that since light has both particle and wave-like properties, that matter should have both particle and wave-like properties as well, obeying that wavelength. And the Heisenberg uncertainty principle, which says that there is a minimum amount of uncertainty for the product of the uncertainty and of position and momentum. And in all these cases, this strange constant, Planck's constant h, kept coming up again and again in all of these places. Then we move on to classical waves, where we looked at the equation of state for a vibrating string, its amplitude over space and time, and found that it is a superposition of normal modes, oscillates back and forth in time, and oscillates back and forth in space. Then moving on to more traditional quantum mechanics, starting with the Schrödinger equation, h psi equals E psi, solving for the wave function, which specifies the state of a system and its energies. We have the Hamiltonian operator, which tells us the kinetic energy and the potential energy of our given wave function. When we solve this for the particle-in-a-box model system, which is a model system for particles translating within some confined region of space, or perhaps the electrons within a pi system of a molecule, we get wave functions which are sine functions and depend on some quantized integer n. And this integer produces quantization and arises due to the boundary conditions of infinite potential outside of this well. And these energy levels increase quadratically with the increasing value of this quantum number n. And this can be used as a model to explain the UV vis spectroscopy of conjugated polyenes and other conjugated hydrocarbons. Then we move on and more formalize the principles of quantum mechanics, going through things like the postulates of quantum mechanics, saying that the only values that we can observe when we measure a measurable property, which corresponds to a linear Hermitian quantum mechanical operator, that the only values we can observe when we measure these properties are eigenvalues of this specific operator for the given wave function. We know how to calculate average properties called expectation values based off of different types of integrals acting on the wave function and the complex conjugate in the wave function being integrated over all space. And we see that the Schrödinger equation, which has its time-independent version here, has a time-dependent version where the wave function evolves over time according to the time-dependent Schrödinger equation, h psi equals I h bar derivative with respect to time of psi, partial derivative with respect to time. Then we look at the harmonic oscillator, which is a model for a vibrating diatomic molecule, or more generally just things that vibrate, and can be used for the infrared spectrum of diatomic molecules. We have a potential which is quadratic, v of x equals 1/2 kx squared, where k is some spring constant and x is our spatial dimension. The energy levels we get when we solve the Schrödinger equation for this system are Planck's constant times a characteristic frequency times an integer n plus 1/2, n starting at 0. And this frequency depends on both the spring constant and the reduced mass of this two-particle system here. The wave functions we get have a normalization constant and a Hermite polynomial depending on this variable 1 alpha to the 1/2 times x, and then a Gaussian function e to the minus alpha x squared over 2. The rigid rotor model system is a model for how molecules rotate. We look at the microwave spectrum of diatomic molecules, which can help you determine the bond length based off of the spacings in the microwave spectrum. There is no potential energy, and we have a wave function which depends on the angular coordinates theta and phi in spherical polar having a fixed bond length, thus the rigid in the rigid rotor, its bond length being rigid. And this gives us a Hamiltonian, which is just kinetic energy, which we reformulate in terms of angular momentum operator squared over 2 times moment of inertia. The energy levels here depend quadratically on a quantum number j, where the energies equal a rotational constant b times j plus 1. And we have 2 different operators for angular momentum: the total angular momentum squared operator, which has eigenvalues of h bar j times j plus 1, and the z component of angular momentum, which has eigenvalues of h bar times the quantum number m. And our total wave function is a spherical harmonic, which in terms of the angular coordinates theta and phi is a normalization constant times the associated Legendre polynomials of cosine of theta times a plane wave or complex exponential e to the minus I m phi for the quantum number m. For the hydrogen atom, we have a model for different electronic states of, you guessed it, a hydrogen atom that usually appear in the ultraviolet region of the spectrum. Our potential only depends on distance, as the proton of the nucleus and the electron interact through Coulomb's law, minus e squared over 4 pi epsilon naught r. The wave functions here depend on a radial part, which depends on the quantum numbers n and l, and then we have an angular part, which is the spherical harmonics, which are the same wave functions we had for the rigid rotor. So the only new part for hydrogen is this radial wave function. The energies we get are actually the same type of energies we observe that in the Bohr model, which also explained the Rydberg formula, but here we get a quantitative version of the Rydberg constant, RH, mass of the electron times its charge to the 4th over 8 permittivity of free space squared times Planck's constant squared times 1 over the quantum number n squared. So the energy depends only on this quantum number n, not the quantum numbers L or m. Going to atoms and molecules more complicated than hydrogen, where we have more than 2 particles, we need to resort to approximate methods due to some difficulties in the Hamiltonian and what the potential energy is. We can't solve it exactly anymore. So these approximate methods we develop include the variational method, where we know if we have some trial wave function, it's always going to have energy which is greater than or equal to the true ground state energy. And we can make this energy depend on some parameter, lambda, and we just differentiate our energy expression with respect to lambda, set that equal to 0, and find the best possible energy we have given this functional form of this trial wave function here. So we try to do the best we can within whatever guess for our functional form we have. We then have the linear variational method, where our parameters in our wave function are linear expansion coefficients for a basis set here. And setting all of these coefficients derivatives with respect to the derivative of the energy with respect to these coefficients, setting those equal to 0, leads to equations called the secular determinant, where we have our Schrödinger equation expressed in matrix form, and we have the Hamiltonian matrix minus the energy times the overlap matrix. The determinant of those 2 differences there equals 0. And we find our ideal coefficients and energies for the linear variational method. Then we also have perturbative methods. In perturbation theory, we partition our Hamiltonian, our total Hamiltonian, into a reference Hamiltonian for which we can solve the system exactly, and a perturbation for which we have some deviation away from this reference Hamiltonian, which we hope is small, and that we can apply successively smaller corrections to our energies. And our energy becomes a sum of the 0 order energy, our reference energy, plus successive higher order corrections, first order, second order, etc. So using these methods, we can then look at atoms with many electrons. The Hamiltonian for an atom is going to be for every single electron. It's going to have kinetic energy, and it's going to be attracted to the nucleus, depending on what the charge of the nucleus is. And all of the electrons are going to repel each other. Every pair of electrons is going to repel each other through the Coulomb force as well. And this is the real difficulty in electronic structure theory, is the fact that you cannot solve for this part of our Hamiltonian exactly, because this is not separable. We can't use separation of variables to solve it as we would for things like a 3D particle in a box or a 3D harmonic oscillator. And then we have other principles that give us some help along the way. We have the anti-symmetry principle, which gives us the Pauli exclusion principle, that when we exchange two electrons in our wave function, the wave function has to switch sign. So what we use to represent our wave functions for these atoms then are going to be called Slater determinants. And then we develop Hartree-Fock theory, where we have the Fock operator, which is a approximate form of our Hamiltonian, which takes a mean field for the electrons, approximates how the electrons repel each other. The Fock operator acting on an individual orbital gives us the energy of that orbital times that orbital back. So the eigenvalue is the orbital energy. And we can express these orbitals as a linear combination of atomic orbitals, and then we get the Hartree-Fock-Rotan equations, where we have the Fock operator expressed in matrix form, and we get the Hartree-Fock-Rotan equations Fc equals ESC, kind of analogously to where we have the secular determinant up here. The electronic states of atoms are represented by term symbols, which tell us about the values of spin angular momentum, orbital angular momentum, and their spin-orbit coupled total angular momentum value J. Then finally, we talk about diatomic molecules, where we invoke the Born-Oppenheimer approximation, saying that the kinetic energy of nuclei is 0, that they're fixed at the origin. Our simplest possible molecule would be H2+, or we can also extend these to H2. That we take the 1s orbital from hydrogen A and hydrogen B, and we see that these overlap both constructively and then destructively, giving us two molecular orbitals, which we represent by their angular momentum eigenvalues and their inversion symmetry. So we have a sigma G bonding orbital adding up density between the two atoms. We have a sigma U star antibonding orbital depleting density between the two atoms and resulting in an antibonding orbital. So in H2, we have a molecular orbital diagram where we have two electrons and we fill up our bonding orbital but not our antibonding orbital. So we have two electrons in a bonding orbital. That gives us a bond order of 1. And we can represent this by a molecular term symbol, which works somewhat analogously to atomic term symbols, except for our value of L, instead of being a capital letter, is now a capital Greek letter. And the term symbol for the ground state of a hydrogen molecule, H2, would be singlet sigma G, or singlet sigma girata.